Welcome to Lesson 4 and the factors that affect solubility. Our lesson objectives: identify the factors that affect solubility and identify the factors that affect the rate of dissolving. So when we talk about things that will affect the ability to dissolve a substance, the first thing we look at is the nature of the solute, what we're dissolving, and the solvent, what we're dissolving it in. And so the saying like dissolves like allows us to easily figure that out. What I mean is polar substances dissolve in other polar substances. So like dissolves like in terms of polarity. So if I have a polar solute, it will dissolve and mix with a polar solvent. And then nonpolar substances will dissolve in nonpolar substances. So a nonpolar solute will dissolve in a nonpolar solvent. Again, like dissolves like. So let's see why that occurs. So looking at polar substances, if we're going to dissolve a polar solute in a polar solvent, why does that work? Why do they dissolve? Well, initially, if this is let's say a salt here, sodium chloride, there are ionic forces of attraction or electrostatic attraction between the positive and negative ions, and that's holding this solid together. And so for water to dissolve it, it has to have a greater attraction between the water molecules and the ions than the ions holding themselves together. So this attractive force between the water is greater and will pull off these ions, the positive and negative ions. How does it do that? Well, if you look over here, you'll see that water has a slightly positive end and a slightly negative end because it's very polar. It's a dipole. And so the negative end is the oxygen, and that's going to pull off the positive sodium, as you can see here. And what that does is it surrounds the ion. It makes new connections, the negative end of the oxygen with the positive sodium ion. And the same thing happens with the chloride ion, but it's opposite. The other end of the water molecule, the slightly positive end, that's the hydrogens, they attract the negative chlorine ion, and they will surround that, making a molecule ion attraction here. So again, the attractive forces between the water molecule and these ions are greater than the ionic attractions holding the ionic substance together. And that's why it can be pulled apart. For nonpolar substances, the reason why they dissolve in other nonpolar substances is because nonpolar substances are not polarized. They don't have these charges. So they have weak attractions or weak intermolecular forces holding our solute together. And so if you place them in a solvent that's nonpolar, those attractions are strong enough to overcome these weak attractions holding it together, and essentially they make new attractions or new connections with the solute. So the solvent is strong enough to pull it apart, again because of these weak attractions holding it together. And once it pulls it apart, it is allowed to spread out, and that is our dissolving process. So again, exhibiting like dissolves like, nonpolar in nonpolar. So then what happens if you take two unlike substances? If you have a polar substance and a nonpolar substance, how come they don't mix? Well, let's look at oil and water, a really common example. Oil is nonpolar and water is very polar. And so since water is very polar, it exhibits hydrogen bonding. So it's the strongest of the intermolecular forces of attraction. So the attraction holding the water molecules is greater than the attraction between water and this non-polarized substance like oil. Since there's no charges on it, there's not a strong attraction, so it cannot overcome the attractive forces of water with itself. So water stays stuck together, and what it does is, as it makes these connections, it pushes oil out of the way. And since oil is less dense, it pushes it to the surface. The second thing we're going to look at is the effect of temperature on how much we can dissolve something. And so we're going to look at solids and gases independently because they are different. So for solids, as we increase the temperature, we increase the ability to dissolve. So for example, sugar in water. If I'm going to add sugar to water, if I increase the temperature, I can dissolve more sugar in the water. But why? This is because energy, heat, is required to overcome the forces holding the molecule in the solid together. Just like we saw when we dissolved the polar substance in the polar solvent, right? We're trying to break apart the attractive forces holding the sugar together, and so the water has to overcome that. and that takes energy. So if we're adding more energy, that means the molecules are moving faster and therefore have more energy to break apart those connections. And so it happens not only faster, but we can actually dissolve more. For gases, it's opposite. As temperature increases for gases, the ability to dissolve them decreases. So example, warm soda goes flat very quickly. But why? Well, at higher temperatures, the particles are moving more and more. There's more movement, more kinetic energy. And that breaks the intermolecular forces and allows the molecules to escape from a solution as a gas. And so if we're trying to dissolve it, that means we want to keep those intermolecular forces of attraction. But because the higher temperature makes them move faster, as you can see here, they're going from slow to fast. If they're moving faster, it's harder for them to make those connections, those intermolecular forces of attraction. And therefore, they can't hold themselves in this liquid state, and they become less soluble, and the gas forms. Lastly, we're going to look at pressure. And pressure only affects gases. If we increase the pressure, the solubility, the ability to dissolve a gas, increases. Why? Well, when we increase the pressure, we're going to force the gas particles into solution and closer together. And as they get closer together, intermolecular forces of attraction start to happen, and we'll pull it into this liquid state. As you can see here, so as we increase the pressure, we're essentially pushing the particles into solution. So as we see here, increased pressure, the particles go into solution. If we decrease pressure, then the particles will come out of solution. So let's check our understanding. Can you identify the factors that affect solubility? Now let's look at the factors affecting the rate, meaning the speed of dissolving, not the amount, not how much we can dissolve like we just talked about, but how fast dissolving happens. And so the first thing is surface area, the area of the surface in contact with the solvent. And so as surface area increases, the rate of dissolving also increases. So for example, sugar granules versus sugar cubes. So if you have a cube, it has limited surface area, so we only have the sides of this cube in contact with the solvent. But if we break it up into pieces, increasing the surface area, we have a lot more of the surface in contact with the solvent. And for something to dissolve, the solvent, in this case water here, has to come in contact to break apart those attractive forces. And so if we have more places to come in contact with these particles, we have a faster rate of dissolving. Stirring also increases the rate of dissolving. Much similar to, I would say, to the idea of surface area. As we increase stirring, we increase the amount of times the solvent comes in contact with the solute, and therefore the dissolving happens much quicker. So let's check our understanding. Can you identify the factors that affect rate of dissolving? At this point, you should be able to identify the factors that affect solubility and identify the factors that affect rate of dissolving.